Okay, Team Statics, here we are again doing some more problems. So this is under the category of equivalent systems, I guess, which is a little bit of a clue. All right, so here we're given this structure, this little L bracket thing, and it's got two forces applied, and the question asks, let me go ahead and include coordinate system. Where would you drill the bolt hole so that if you attach this to something, it doesn't rotate? So basically, imagine you're drilling a hole somewhere here. You're going to attach this to something else, and then I want you to figure out where you need to drill it so that it doesn't rotate. Let's go ahead and pause, take a quick look at the problem. I can even try and zoom in for you a little bit so you can see clearly the diagram, and come back. I've got some music playing in the background. Hopefully you can still hear me over that. So let's talk about the approach for this problem. Basically, we want to remember that any force system can be replaced by an equivalent resultant force. So let's first consider actually a simpler version of this problem, just to get the concept of how you should approach this down using the idea of equivalent systems. So basically, the bolt is going to be the equivalent system that when these forces and moments are applied, right, you don't get any rotation, so the moments are going to actually be balanced out. So let's just go over that conceptually. So let's say we just had a box, right? And we'll apply a moment up here somewhere, and we'll apply a force right here, and give it some distances. So that force right here, we'll call this one B, this one we'll call A. And so we'll ask the same question, right? Where do we need to put this force, equivalent force, so that that moment is canceled or equivalent? So can we replace this thing with an equivalent system? So if we do, we need a coordinate system. X and Y. This is pretty trivial. Here we're just looking at the resultant forces. So sum of forces is going to just be equal to F. And let's draw an equivalent system. So what we're basically asking is, can we replace this thing with just a force, right? Some force such that if we took the moment about a point, let's pick a point here, O, you get the exact same answer, right? So there's going to be, this is going to be located some distance y, right? Assume we have the same coordinate system. So from a sum of forces x point of view, we're still good, right? F is still just equal to F, right? No matter where we put this force, anywhere along this box on the right-hand side, we can get F. Now let's do sum of moments on the left-hand side. All right, we'll go positive counterclockwise. So we have a minus m minus f times b. So that's the resultant moment on the left. So what is this resultant moment on the right going to be? Sum of moments, again minus f, but now times y, right? And y is the unknown. That's really what we're after. Where should this be, right? And the point here is that these moments should be equal in order to cancel the m's and avoid spinning. So let's just do that. So the minus m minus fb from the left-hand side basically needs to equal minus f times y. And then we can solve for y. Right, pretty simple algebra here. It's equal to m over f plus b. So dimensionally we're okay. A Newton meter divided by a Newton will give us a meter, plus b, whatever that distance was in meters, will give us a location value. So now the question is, does the x location matter? So pause and think about that. Okay, now that you're back, curious if anybody actually really pauses. So what I'm asking is does it really matter where we put this force? So these are all knowns here, right? In this equation, M would be given, F would be given, B are given, right? Otherwise we cannot even solve for Y. So now the question is, does it really matter, once I know Y, where I put this force F? So I'm drawing up on the diagram in the top right. Can I put it here? Can I put it here? Does it really matter? In this case, no, right? Because the moment and the force F the moment due to that force F is acting in this one direction, right? So prove that to yourself if you're not convinced that for any X location along this box, you're going to be able to balance out that force, or the moment, excuse me. Okay, so now let's go back to our more complicated problem and apply the same principle. So I'm going to just grab this system here and copy it down. All right, so what am I going to do? First thing I'm going to do is sum the forces. So we have forces acting both in X and Y. So we have F1. I like to use the inside angles. I just find it easier. So I'm going to call that beta. We're going to solve this problem symbolically. 180 minus alpha. So I'd put that into MATLAB just like that. And then I have beta defined. F1 minus F2 sine beta. And this is basically equal to our Fx forces. Sum of forces y. Nothing from F1, and then we have minus F2 cosine beta. So this equals Fy. So what that means is we want to know where are we going to put this bolt hole that's going to balance, give us the balanced forces on this side, and that doesn't allow for any spin. So I'm going to remove actually these forces here and this stuff here. I'll leave the external geometry. But I basically am asking you, where do we need to put this thing? Is it here? Is it here? Is it here? So I'll just pick a spot for right now and just label it X and Y with X and Y dimensions. So this will be X, and this distance will be Y. And I know I'm going to apply this resultant force here so that I can make sure I have my resultants correct. So Fx and Fy, looks like it's going to be negative. Don't really know the sign of Fx until you put this in, but it really shouldn't matter as long as you're consistent with your calculations, right? So we have some resultant force, right? So Fr Fx plus Fy. That's more of an FYI. All right, so we know that these forces are going to check. Sum of forces y, check. But now what about the sum of the moments? So let's take the moments from the left-hand side. And let's go ahead and pick this point O down here in the bottom left again. I only picked that because it's convenient. And one of my lines of actions, F2, the vertical component, right, is going to go through that, so that'll cancel that in the equation, making it only slightly easier. So let's do sum of moments to O, positive counterclockwise. What am I going to get? The X component of F2 is going to contribute to that moment, so F2 sine beta times its moment arm A. The Y component does not contribute, it intersects with point O, minus F1 times its distance, A plus B, plus M2 minus M1. So this is equal to the moments on the left-hand side. So this is what you throw into MATLAB and you should come up with some number, right? And what are we trying to do? We're trying to figure out the X and Y locations on the right-hand side to make these two equal. So we'll take the sum of moments, this is on the right. And what we're going to get, right, is simply at first minus Fx times Y minus Fy times X, right? And now this is equal to the moment on the right-hand side, and we want these two to be equal. So we'll set them equal to each other. So we'll go ahead and, we don't know this, right, value here, the moment on the right-hand side, so let's substitute in a few things that we do know. So we have minus, substituting in for fx, it's going to be whatever this number is, f1 minus f2 sine beta, minus, and fy is a minus f2 cosine beta times x. Right, so this is the moment on the right-hand side. And now I'm going to set these two equal to each other. So really, I'm setting the left-hand sides of the equations equal to each other. So minus f1 minus f2 sine beta plus f2 cosine beta, go ahead and cancel out that negative, and this is going to be equal to the moment on the left-hand side. Again, this is a number that you calculated in MATLAB. Oh, and I forgot a y here. And now what are you starting to see? So if we go ahead, right, and start simplifying this, we're going to have minus f1. Actually, let's do it this way. I'm going to bring the y to the other side and the moment to the other side. So f1 minus f2 sine beta times y is equal to f2 cosine beta times x minus the moment from the left-hand side. So I pulled the left-hand side over this way, and I pulled this one over that way. And what do we have? Y is equal to f2 cosine beta divided by f1 minus f2 sine beta times x minus this number, whatever that was, divided by f1 minus f2 sine beta. So now what you see here, this is the equation of a line. And anywhere along this line would prevent rotation as long as you can actually drill the bolt there, right? So given the coordinate system, right, it's saying that anywhere along this line, somewhere, if this was actually the equation of the line, for some value of x, you could then predict what the value of y would be, and anywhere along that line, you'd have this centered up, and it wouldn't spin. That's how you solve that problem.